While the legal slide is up, I'll introduce myself. My name's Brock Taylor. I am also part of the Intel Champaign-Urbana contingent. There's actually quite a few of us here. So hopefully everybody watched Bill's keynote just a few minutes ago. Christina's yesterday. I actually sit very close to the both of them. We're all in close proximity there in Champaign, sitting very close to the corn and soybeans. A little bit about myself before I get into the talk. I helped create and actually curate the Intel Cluster Ready architecture, which we launched in 2007. And since then have really been focused on trying to simplify access to HPC clustering, make it easier, and work with a lot of systems vendors, application vendors, and middleware providers to try and provide what we would call volume or more small-scale HPC clusters, the industry, make it easier. So through that, we've done a lot of various things. Bill mentioned Intel Cluster Checker. My group actually developed that tool and produced it, launched it in conjunction with Intel Cluster Ready. And we'll actually highlight that a little bit and how it's going to tie into some of the things. But essentially this talk is in some ways a summary of a lot of the different sessions that are going on throughout the conference. So in many ways I get to be a thief and steal people's slides throughout here. So I'll highlight a number of things in there, but ultimately it gets down to really talking about what Intel is doing and how we're working with the community to start to address a lot of the problems that are coming. And as I said, some of the work that I've been doing over the many years is working in small-scale HPC or smaller types of systems, call them application target platforms. Last year, when we announced the march to deploying Aurora in Argonne, that introduced a whole another set of problems that we have to go and address as a company and really as an industry, and that's to hit a lot of the growing challenges that are coming. Specifically, there's a lot of bottlenecks as we march towards exascale we have to address, and there's a growing divergence in infrastructures, right? It's not just HPC, it's moving to big data problems, visualization problems, machine learning. And all of these different types of environments are requiring different types of systems or different types of infrastructures, different types of setups. And so that becomes a challenge of how do you manage that divergence in a productive manner so that you can reuse solutions, you can reuse the components. And then there's new use cases, right? How do we bring in more people? Many years ago we'd actually talked about small clusters being an entry point into HPC. And somebody actually made the comment, maybe cloud is the entry point into HPC for a lot of people, right? It's not having infrastructure locally. So there's new use cases that are emerging. There's more and more interest of HPC in the cloud in those types of environments. So all these things are feeding this rapid pace of technology innovations that are coming into the marketplace. We're feeding a lot of those through a lot of our components, and that has a direct impact on HPC developers. One of the things that both Christina hit on yesterday, Bill hit on a little bit today, as a developer, as an HPC developer, it really gets down to where are you spending your currency. And currency may not be dollars or euros or money. It may actually be time. It may actually be resources. Bill said something that's been a mantra for us for a while. It's we want the domain experts operating in their domain. Right? Scientists should be doing science. We don't want more time spent on just getting the systems up and running. And that was something that on the small scale was a huge problem for many, many years that we were trying to address. Now it's becoming bigger and bigger. Again, all the divergent types of solutions that are coming, all the new technologies, all this pace. So as developers and as researchers, where are you going to be spending your time, right? Where are you going to be spending your money? How do you budget that? What's the return on the investment that you put in to those investments or those changes? Are you going to get what you want out? So if you put in a lot of time and you get a couple percentage points of performance increase, is that worth it? Take yesterday's example in the CERN challenge, where it's a 220 plus times increased. That's a pretty good return on investment, I think. So we're looking at those kinds of things and trying to see what can we do to help, right? As well, you can think how fast things are moving, what you're doing today, and what you're building for today, what you're developing for today, maybe something's different in the future, right? Bill mentioned the change from more of small core systems to many core systems. That really hasn't happened that long ago. So how many people were actually thinking 10, 15 years ago when you're writing your codes, this is the environment I'm developing for, right? This is where we're headed. This is where we're going, and actually thinking through that. So it's these things that come out, these new innovations that are coming very, very fast when they get introduced. Are you ready for them, right? Did you know about them? Did you plan for them sometimes years in advance, right? Many of these things, there's not ways to plan for that, right? The innovations come in, so you need some mechanism that can help with that. But those early decisions in the development process can have long-lasting impact, right? So again, yesterday, the example of the guy doing brain research, obviously extremely smart person, but is more of a serial code, right? So somebody's able to come in and actually dramatically do a speed up on that code when you do the code modernization, right? So we've looked at this, and we've looked at what can we do to help this problem. And Intel is, in many ways, well positioned to address this because we have so many components that we provide, and we have a lot of connections within the ecosystem and within the community to really be able to provide what we would call a holistic approach to address the issue. And that is what Intel Scalable System Framework is about, right? So it's how do we bring all the things that we have, how do we work with the community, and how do we work with the ecosystem to actually come up with some process, some mechanism that makes it easier to address these challenges, both as developers, as technology innovators, as an ecosystem together, right? Bill hit on the four tenets of Scalable System Framework. We're really looking at how do you go from the small scale all the way up through supercomputing. So again, things that I've been doing for years in the small end, things that we're doing to deliver Aurora, and everything in between. We've got to figure out how do we produce solutions that people are able to tap into, able to use that. What are the workloads like, right? There's compute intensive, there's data intensive, there's lots of things. So we've got to figure out how we address that and bring in all the technologies that we provide in an efficient manner. That really gets down to, we're looking at standards-based programmability. That's a hard word to say. What do we do? How can we build on something that, again, gets the community involved and we maximize that leverage? As we're bringing new things in, we want people to be able to take advantage of it as quick as possible. We want existing codes to be able to take advantage of new technologies that come in without changes as much as possible. So again, how do we do that? Scalable System Framework is our approach to help do that. And that's also, as I said earlier, addressing the growing types of usages, right? The increase in cloud. How are we going to bring that into play? So at the bottom, you can see we've got lots and lots of different components, elements, technologies, expertise that we're providing in, and we're reaching out more and more to different areas of the community to try and pull them in. And I'll talk about a few of those things as I go through this, and then near the end, hit on a little bit of the plans of what we're doing in the short term or the near term, some ideas. I will say that there's going to be a lot more information that comes out of this, out of the supercomputing conference and in the coming months. So I'm not going to be able to go through everything today. Hopefully we'll have a little bit of time for questions. Hopefully I'll be able to answer some of those at the end. But I'm sure there will be things that I won't be able to answer yet, and there's various reasons, but a lot of information is coming soon. So I want to look at some of the things that we are providing. Again, you'll hear a lot of these things throughout this conference, throughout supercomputing, and pretty much a lot of the bread and butter things that we provide. On the left-hand side of this slide, it's obvious the processors. New in recent years, it's not just one type of processor now. We have two, Xeon and Xeon Phi. Hopefully you're familiar with the software elements we provide in Parallel Studio. Intel Luster is becoming bigger and bigger. Now we have the fabric, we have storage, and memory. So a lot of different components that we're actually providing into the ecosystem. And we want to make sure that we're doing as much as we can to let you take advantage of them as fast as you can. Right? So what I want to do is actually kind of walk through some examples where I tie in a number of these components together just to show you what's coming in the near term or is already here but just announced, and use that as an example of why we need Scalable System Framework and how these things are going to be introduced in, and then get into a little bit of the thinking of how we're going to do a better job of introducing things holistically to you. All right, so first thing I want to look at is Xeon Phi, specifically with Knight's Landing that's coming. There's some pretty big elements to this. Bill hit some of those in his keynote, and again, there's other sessions on Xeon Phi, and there's a lot of information that's coming out during supercomputing. But I wanted to talk about a few things in particular. One is this is going to be the first Xeon Phi that's a processor, not a coprocessor, or have an option that's a processor, right? That's a big change, right? Now you've got a system that's actually running a Xeon Phi system instead of a Xeon that has a host Xeon Phi inside of it, right? There's also going to be an option with integrated fabric, right? So now you've got not only a processor, but you've also got integrated fabric, and you still have the card, right? So we want to make sure as we introduce this into the marketplace that you're also able to run your existing codes, right? That's a big element. So your existing codes that are running on Xeon are still going to run on Xeon Phi, right? So there's a binary compatibility, that element, but you're also going to be able to start taking advantage of the new features in Xeon Phi, and that includes things like MCDRAM, which Bill talked about, is a dramatic improvement in especially workloads under heavy use, right, are going to see huge jumps in the latency. We also have Omni-Path architecture, right? Intel Fabrics. But Omni-Path coming out has a number of different things. It's a pretty wide portfolio of products in and of itself. In the adapters, the switches that are actually going to offer more ports per switch for your edge switch, which relates to lower cost. You're able to get more servers into the rack, a single switch. You've also got the director switches to tie larger systems together, and even options to integrate the silicon or have custom designs with the OEMs, right? The one thing I want to highlight is, again, you're talking about integrated fabric. So the Knight's Landing with an integrated Omni-Path fabric gives you all these different options, right? So this was coming from a talk again yesterday that Jim Wright gave. If anybody was able to see that, just highlighting some of the elements that we can expect, a little more of this integration to occur over time, right? We're going to get more and more because you get benefits like lower power, better performance, lower equipment costs out of these types of innovations. And we want to make sure that as we do this and you're introducing it, again, a key point, let you take advantage of these improvements transparently, right? So that highlights the need that we have a good standardized API, or the API is extremely important to make sure that the existing codes today will be able to take advantage of the new architectures of the future. So a little bit more. Yeah, okay, sorry. Again, I'm making sure the slides are advancing. A little bit more on that. If you're using some of the existing elements like the performance scaled messaging, the PSM layer, you're going to continue to be able to use that. It's still going to be supported. But one of the things that we're doing is, as we make improvements, we're making sure we're building on top of the standards, right? And that is using what's available in the Open Fabrics Alliance and actually contributing a lot of work into that, right? So the key point of this slide, of Jim's slide, was really the bottom of the slide, and it's that message of don't lock yourself into an API that can't evolve. And so we're taking that to heart with our fabrics. We've really got to look at how do we make sure that as the fabric innovations are coming in, the existing codes keep working. And that is ultimately feeding in a lot of code and expertise into the development of libfabric or the Open Fabrics interface. And so we actually have Sean Hefty from Intel is one of the people that's feeding into libfabrics and providing his expertise. He actually gave a talk yesterday on this, so I robbed him of this slide. But he's also giving a tutorial on OFI at supercomputing that's tomorrow. But essentially it's exactly what I've said about 3 times now. We're trying to build in that expertise so that people are able to take advantage of it, right? And then as the innovations come in, it's going to make it easier for people to transparently get the value that we're bringing to the table. Another element that's related to both Fabric and Knights Landing is the way offload works today, right? So if you've got a Knights Corner system, you're using offload. It's basically running on a Xeon and then offloading to the Xeon Phi that's inside the system. Coming in the future, we're actually going to have that offload capability over the fabric itself, right? So again, the existing codes that are running offload today are going to transparently work with Knights Landing and separated machines tomorrow, offloading over the fabric, right? That allows data centers to have more flexibility in the types of systems they've got. So you can, as this diagram shows, you can actually have Xeon systems, you can have Xeon Phi systems with added in fabric, and you can have integrated fabric as well. So it gives a wider range for data centers, big and small, to actually have a mix of systems to kind of address that growing need of different types of workloads, right? Again, HPC is different than big data and visualization. Also, it's opening up avenues that we didn't have today or that we don't have today. Again, providing them in ways that we can introduce the technologies as fast as possible with as little impact to existing codes and as fast a path to get better over time. One more slide on Fabric, and then I'll move on, I swear. This is, again, highlighting that we're striving to keep an eye on what's going on today and introduce things over time. But again, it's the binary compatibility. This is a deeper dive into what the fabric layer will look like. But as you can see, there's the elements of the different types of MPIs that can leverage the fabric, making sure we maintain that over time. Right? Again, with the theme of keeping things moving as fast as possible. I wanted to mention Crosspoint, in 3D Crosspoint technology and Intel Optane technology. Intel Optane is actually a combination of 3D Crosspoint technology and some of the non-volatile memory controller technology, but together is actually providing some really interesting elements that I think are in the future really going to change a number of things, right? The performance that you can get out of having this type of memory, very large scale in a system, is really interesting to a number of workloads. In fact, I was having a conversation last night with somebody at dinner. We're talking about some life sciences workloads that are very heavily I/O, and having this type of memory where you can actually load very large databases, if you will, into memory is really going to change some of those codes, how well they perform, what you can do with those codes. And I think it's, when you combine, oops, I did not do that. Cheated. Stealing my thunder. That was one of the best slides too. All right. Dang it. So anyway, it's really exciting. I think one of the things I like to say is it's not what we know we can do with this technology, it's what we don't know people will do with this technology. It's the new things that will come, and that actually helps feed a virtuous cycle into putting more time into finding the right innovations in the technology and the right things to do. So, all right, I'm going to go to the next slide, which I'm purposefully not going to talk too much about, because right after this session, Carl is going to be talking about OpenHPC in much more detail. But this is a really cool thing that has come together in the past year. A lot of people at Intel, a number of them in this room, have put a lot of effort into helping get the community together and start this. So we've got a number of partners here, and honestly, it's changed since I got this. There's even more founding members that have been a part of this. So ultimately, OpenHPC is a software stack that has lots of different components in it. It's not just a software stack. It's build mechanisms. It's ways to ensure that the entire stack is working together. It's a huge effort, and it takes a community. And we've actually got a lot of really good community members that are coming in, contributing to this, and have helped get it launched. Just literally was announced on Thursday. This is going to be a really big base and a foundational element of Intel Scalable System Framework, because it provides a lot of those standards, a lot of those things that we've got to build on if we're to capture and transfer a lot of the technology, right? So again, right after this, Carl will give a lot more details on this, so I'm not going to steal his thunder too much, but it's a really exciting thing for us and for the community, we hope. So from here, what I want to talk about is how are what's our thinking in terms of what are we planning with Intel Scalable System Framework to kind of package things up a little bit. And one of those elements is providing what we call reference architectures, right? So a reference architecture is more the blueprints that we'll use to provide targeted solution platforms. And you can think of the first one we're likely to do is the classic HPC cluster, because it's very familiar and it's one that's broadly used. So a very basic representation in the graphic, not a graphic artist, so it's not a very flashy type of graphic, but we're talking about something that has a head node fabric, maybe one or multiple switches, but then compute nodes and some storage. But it's something that's well defined, so it gives us a good base point to introduce, right? So we'll probably start with that, but what the reference architecture will do is define what building blocks do you need, what are the requirements, what are the configuration elements that you have, and put the parameters in place, really define this is what that classic system looks like, that classic HPC cluster. From there, we want to provide reference designs that provide examples of how you can actually produce something of that reference architecture, right? So it's a specific set of hardware and software components with defined integration steps, right? So in this example, again, a reference design would be a recipe that combines a set of Intel components into that classic HPC cluster. And here you could think, this is a Xeon-based cluster. It uses Omni-Path. It has Lustre and Intel SSDs, and it uses a software stack that's based on OpenHPC, right? So the reference design would go through and actually define how all those components go together, what it's done, and actually also give you at the end a fully working system that you could use, right? Now, it does mean that because it's a specific set of components, we're likely to do multiple reference designs for a given architecture. In the future, we'll actually start to expand both reference architectures and reference designs that go with them, right? So again, as we look at what's big data look like, what does machine learning look like, what does visualization look like, we'll start to look at defining architectures, reference architectures, and producing reference designs. We do that now with a lot of different elements. So I mentioned Omni-Path. We have reference designs on Omni-Path. In small scale, we have Intel cluster ready reference designs. We have lots of different things. We're going to look at how do we combine that a little bit better, right? How do we make these things better? And using things like Open HPC software stack and the Intel components, pushing these things a little more collectively out into the world. Does it make sense so far? Another element of that is providing the means to verify that what you have actually meets those architecture definitions, right? And that is where Intel Cluster Checker comes into play. We've actually had this tool for a while. This year is the introduction of the third generation of tool as an expert system tool, which is an expert system is something that's provides a little more diagnosis based on elements that it finds. So you can think of, if you know what WebMD is or some medical systems, it's basically looking at different things that are wrong and then coming up with reasons or a diagnosis of, hey, this is what the root cause of a problem is. We introduced that this year as a way to make it easier for people who didn't have really deep cluster expertise to understand if there were issues going on in the problem, what those issues were, and get to the point where we could actually tell somebody, hey, this is a problem in your system. Another side of that is the ability to go in and check what is on a system and actually compare it to a defined architecture, right? So that ties into, as we produce reference architectures and reference designs, we're going to be able to use Cluster Checker and extend its capabilities to go in and say, you've actually met this reference architecture, right? You actually have met all the requirements and have all the building blocks that are needed for the classic HPC system or the new reference architecture of the future. Okay? Another capability of Cluster Checker 3 that we've introduced is the API for integration. So not only can you check this from a systems level, an application is going to be able to go in and make similar queries, right? So if you're an application that lives in one domain and you want to verify that you're going to run on something that meets a specific architecture, you're going to be able to hook Cluster Checker 3 to go in and make those queries and find out before you run. And so there's a number of elements. We've worked with some application vendors on that this past year, trying to hook Cluster Checker a little bit more, and we're finding that there's a lot of momentum and actually a lot of effort that was going on of people doing that on their own. Now Cluster Checker is going to be able to do that and help them with that. So at the end of the day, why are we doing this? Go back to at the beginning, I was talking about wanting to provide the value, wanting to address the problems, help developers with the entire life cycle of their codes, right? We believe that this approach is actually going to help extend the investments in existing codes, right? Again, so where you spend your time, what you're doing, what you're getting out of it, how much do you get out of doing code optimizations, right? If you need to spend more time on the research, we want to extend the time of the existing codes. But we also want to simplify the adoption of all the new technologies coming in so that when you're ready, you can get those 10 times speed ups or 220 times speed ups of your code, right? So when you're ready to make those investments, we want to simplify the path that allows you to take advantage of all the new technologies that are available. We also want to reduce cross-platform validation, right? So as you get a little more standardized interfaces and things, it helps to move from platform to platform, right? So again, if you're working on your laptop, right? And a lot of times you're developing on your laptop, you're moving to a small cluster, right? What's that portability, right? When you move from that small cluster to a really large cluster, what's that portability? When you move to a cluster in the cloud, what's that portability? A lot of commercial ISV, commercial application vendors, they have to test on all the different platforms, right? What if the OS is different on every single platform? Well, they have to test that as well in the matrix, right? So it quickly builds. We want to reduce that with Scalable System Framework, right? And then finally, we want to expand adoption. It's make it easier to tap into these resources. Right? Get more users who are able to come in and run these applications. About a year and a half ago, I was able to attend a small conference called Hub Zero. If anybody is familiar with Hub Zero, they have a hubbub conference every year. And Hub Zero is something that started out of NanoHub at Purdue, I believe, and it grew into a little more of an interface to compute resources. And one of the things that a professor talked about was how his students are becoming less and less, he said, sophisticated in the technologies underneath. But he had students that were coming in and doing studies on lava flows, and able to run simulations directly by going to a web interface through Hub Zero and connect to compute resources that actually did the simulations. And those students didn't know anything about how the simulations were done. They were literally going in to get the answers, right? They could put the parameters in and get the answers out on the other side and use that in their research, right? That's science. Scientists doing more science, right? Those are things that I think we're going to see more and more of over the years, and again, part of what Scalable System Framework is meant to increase, right? So I will actually conclude with the tagline, watch this space. Again, there's a lot more information that's coming. I'm actually not able to provide everything today. You'll get a lot more throughout the week if you're here at Supercomputing. If you're not, there will be more that comes out through Intel's website and other avenues as well.